In this video, we'll have a look at the matrix dimensions of the equations associated with MLPs. Getting these straight is crucial when you want to implement MLPs, so this is particularly relevant for your assignments. Let's dive right in. Matrix dimensions. So we'll start with the simplest case, where we have one neuron and one input vector that goes into the neuron. So notice that here x is lowercase, meaning that it's just a single input vector and not a matrix. Later on, we'll have a batch of data points as an input, and then we'll have a matrix, and it's going to be capital X. So the input vector here contains several different scalars, k-scalars in general, here 3. And for each of these inputs, we're going to have a weight that we multiply with it, and we also add a weight in order to get our pre-activation. So we can write that as this formula, and then the second computation that happens in the neuron is this application of the nonlinear activation function. Now, looking at the matrix dimensions, we have this vector of weights, so this here, times this vector of this input vector, plus the scalar bias. So in the notation that we use here, all our vectors are column vectors. So what that means is that the weight vector here is actually W transposed, and the input vector is just X. And then the scalar is, of course, just a non-bold-faced B, meaning it's just a scalar. So checking the matrix dimensions, here we have a 1 by 1 scalar. We have a 1 by 3 vector times a 3 by 1 vector. 1 by 3, that gives a 1 by 1 matrix, which is a scalar, plus a scalar. So we're checking out, we have a 1 by 1 matrix. And of course, the activation function is applied to this 1 by 1 matrix, which is a scalar. So that remains a 1 by 1. Now let's have a look at this slightly more interesting case where we have 2 neurons and 1 input. And we'll still have, in each of the neurons, we'll have a scalar pre-activation and a scalar activation. And the same for this neuron here. The one thing that changes compared to the situation with just one neuron is that, well, we have a weight vector going into, well, being multiplied with the inputs to go to the first neuron, and we have a different weight vector being multiplied with the inputs to go to the second neuron. And then we can actually write these equations like this. This is exactly the same types of equations that we saw before for a single neuron, and we have the same equations now for the second neuron. And now that we have these two outputs, we can actually stack them together and write this as a matrix vector valued equation, as a single equation. So to do that, we'll have our output Z. Well, that's just going to be Z1 and Z2 stacked in a 2 by 1 matrix, 2 by 1 vector. We have the W transposed. That's going to be the W1 transposed and the W2 transposed stacked on top of each other. And then we have the bias vector, which is going to be W1 and W2 stacked on top of each other. And then we just apply the activation function here to every element of Z in order to get the activations, and that's again stacked H1 on top of H2. So the visual illustration for this is as follows. We have the 2 by 1 output, Z, as I mentioned before, is this 2 by 3 matrix, which is the first weight, W1 transposed, and the second weight, W2 transposed. We multiply that with our 3 by 1 input vector, and then we add our 2 by 1 biases. So checking the matrix dimensions again, we have 2 by 3 multiplied by 3 by 1 gives 2 by 1, and we add a 2 by 1 bias, and that checks out with a 2 by 1 result. And then, of course, the activations are just the activation function applied to each of these elements of the pre-activation vector. All right, let's now move to the most complex case here, where we have multiple neurons and we have multiple inputs. Now X is uppercase, so we have not just one input, but we have multiple such inputs next to each other. And now we also have the case that these pre-activations and the activations are vector valued because you have such an activation and a pre-activation for each of your inputs. Again, we can write these equations here for one neuron at a time. The only thing that changed here now is that, well, the Z's and the H's are now bold-faced, so they have two elements in there. And the X is now this capital X, which is just this entire matrix. And again, we can write this as one equation. Now we have a capital Z, that's a matrix. That's namely stacking this Z1 on top of this Z2. And we have a capital WT as before, that's stacking W1 transpose on top of W2 transpose. And we multiply that with the input matrix as before. And then again, the activations we get by just applying the activation function element-wise to every element in Z. All right, looking at this visually again, now we have a 2 by 2 output. So that's stacking, sorry, not this, stacking Z1 on top of Z2 that we get by having these two weights, W1 transpose, W2 transpose, times the input vector 1 and the input vector 2 put next to each other in a matrix that is a 3 by 2 matrix. And in the end, we apply the activation functions. Now, if you're really attentive, you might have seen that there's something fishy going on here. This here is a 2 by 2 matrix. That's a 2 by 3, and that's a 3 by 2. And 2 by 3 times a 3 by 2 gives a 2 by 2 matrix. But this here, that's only a 2 by 1 vector. And well, that's because typically there's one bias for each neuron, and you're going to have the same bias that you apply for every one of the inputs. But nobody tends to write down the biases as a matrix. So what's going on is the same as broadcasting in Python. So we interpret this as this input vector here being interpreted as a matrix. So this wouldn't work in linear algebra, and in order to make it work, this 2 by 1 vector is broadcasted into a matrix that's 2 by 2. And then the matrix dimensionalities work out, and everything is fine. Now, so far I talked about the notation that we use in the slides, which is also quite common in most papers and also, for example, in the deep learning textbook that we use a lot. But in deep learning frameworks like PyTorch and TensorFlow, data points are actually row vectors, not column vectors. And since we will try to follow that notation in our coding exercises, I do want to briefly tell you what changes in the notation in that case. Now in PyTorch, the input matrix has n data points in the rows and d features in the columns. So each of the rows is an individual input, and the features are in the columns of X. A single linear layer then has a weight matrix W that is m by d, so the number of units times the number of features. And we have one bias for each of the units. That bias is then expanded using broadcasting to an n by m matrix by repeating it for every data point in the batch. And then putting it all together in the formula for our output, we now have X W transposed, which has dimensionality n by m, and we add the broadcasted bias of the same dimensionality. So when you look at things at the code level, please do keep those changes in the notation in mind. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions to think about for yourself. So thank you, and I'll see you in the next video.